Cellarosi, and we'll talk about limit theories for theta sums and applications.
Thank you very much. So I'll be using a more primitive tool for presentation. And I will mostly talk about parts of my thesis as a grad student here at Princeton under the supervision of Professor Sinai. Okay, so I want to start with application, like one baby example where one can see already a lot of interesting things going on. So the application I have in mind, it's autocorrelation function in quantum mechanics. So I'll work out an example that anyone probably saw in quantum mechanics 101, like very simple example. So application. And then I'll tell you later about these limit theorems. So let's consider a free quantum particle on the torus, on the one-dimensional torus. And the evolution, the quantum evolution, if you choose properly units such that h bar equals twice the mass of the particle and equals 1, the evolution is given by a Schrödinger equation of this form. So x is the position in the torus, s is time. For some reason, I like s to be the time. This equals I and then there is periodicity. So that's a Schrödinger equation. This gives the evolution. And this Hamiltonian h equals minus has eigenvalues En equals to 4 pi square n square, n equal to 0, plus or minus 1, plus or minus 2, and so on. And eigenvectors, eigenfunction, phi n x equal to 2 pi I n x. Okay, so if you want to consider the evolution, like the solution at time s, so the solution at time s, so we need an initial condition, so it will be, that's the initial condition at time 0. We can use this. This is an orthonormal base of eigenfunctions for this Hamiltonian. So we decompose the initial condition in eigenmodes, basically. Those are we do this. And then we evolve each mode separately, and then we take a linear combination. That's basically how the evolution works. So the solution of star is psi xs equal to the sum over n. Then we have our coefficients, and then we evolve each eigenmode separately, and we use a simple evolution operator, which is e to the minus I e n s times psi n x. So this is basically an operator. So this is very classic, and an object that I want to consider is autocorrelation. What is autocorrelation? So it will be C of S. Basically, so here we have a wave packet or a function that moves according to some evolution. So we want to know how much, we want to quantify how much the particle or the function at time s remembers of the function at time 0 in some sense. In other words, we take the expectation of this operator with respect to the probability distribution given by the initial condition psi naught. So formally what we look at is the Cn e to the minus I e n s. Sorry, Cn squared. So this is autocorrelation function, And basically it does what I just said. So it gives you somehow how much the particle remembers at time s of its initial condition. So you can imagine this is a fluctuating function. So now I want to consider, so suppose a very specific case, a very particular case of initial condition. And since here you see limit theorems, something has to go to infinity. So I'll choose a large parameter, and it works this way. So I take an initial condition that depends upon a large parameter. So that's our initial condition. And it will have this form. 1/2 sum over k f of n x minus x naught minus k. So what's going on? We fix like a profile function, let's say Schwartz, and let's say of norm equal to 1. So we fix the shape of the initial condition. And this basically, this large parameter, what it does, it concentrates the initial condition around the point x. So capital N is basically the strength of the localization. So you can think of this is my initial condition with given n, and then when I increase n, it gets more and more peaked. And this is chosen so that the normalization stays. Everything is of order 1. Okay, so this is my initial condition. So if I do this for this initial condition, you can compute explicitly what the Cn are. They will depend upon the Fourier transform of capital F. I don't want to give you the details. But in this case, C of S, which will depend on n, of course. In this case, this correlation function is of this form. N to the minus 1 sum over n f hat n over n, and then my eigenvalues, like here, e to the minus I for pi square n square s.
What is the sum over k?
Basically, it's just a way to so you can think of f as a fast decreasing function. So only finitely many k will come, basically.
Oh, it's not to make it periodic.
Yeah.
Oh.
But basically, it's, yeah. So this is our autocorrelation function in this case. So it is true that this is a 1 over 2 pi periodic function of S. Okay, so a question that I want to ask, which is kind of natural to ask, and by the way, this function, when n increases, becomes more and more like ugly. So you can think of this as the period. The function becomes like very, very complicated. Okay, as n increases, you can see it from the formula. So the question one can ask is, how often is this function, let's say, above a certain limit? How often does the particle remember as much, in a sense? So how to say that? So I pick all the point in time in the period such that, for example, my correlation function exceeds some value. But I have to rescale things because the correlation function is going to 0 with n going to infinity, so I have to rescale. But in the proper scaling, I ask, how often does the particle remember as much? Okay? And of course, I take the set of such S, take the Lebesgue measure, and divide by the length of this, which is 2 pi. And then I want to take the limit when n goes to infinity. Okay? Does this quantity exist in the limit? And how do we compute it? Or, second, like, same type of question with analog answer. You can look at the same quantity. So instead of looking at n, you can look at n over 2. And n at the same time. Okay, so you can look at jointly. Basically, you're following two particles with the same shape but different type of localization, different strength of localization. You want to see if jointly they have some limiting behavior. Okay, So the answer to these limits is yes, they exist, and they follow from the following theorem. Let me hide this for a second. Theorem. Well, first let me introduce what's a theta function, or theta sum in this case. So what's a definition? A generalized theta function, theta sum, is the following. So let me write here. So it's S n f alpha, which I mean sum f n over capital N. Here is n in z, and then is e to the, say, pi I n square alpha. So you see that little f is basically absolute value of f hat square, and alpha is whatever, 4 pi s. So you see this is the same shape. You have to rescale this by n because you want to match this thing, but that doesn't matter. Okay? So the theorem from which the existence of the above limits follow is the following. So fix, let's say t, which is an array of numbers, let's say t1, t2, tk, for example. So fix these numbers, and I claim that there exists a probability measure on c to the k. Let me call it p tf, such that for every nice open set A in c to the k, the following is true. If I look at the measure, doesn't need to be the Lebesgue measure, but let's say lambda is the Lebesgue measure. The measure of alpha such that, so here the periodicity is a bit different, but doesn't matter. The measure of alpha such that, so now I take S, F, T1n. So this is a complex number. This is a complex number. Then I take S, T2n. This is another complex number. And so on, S, Tk, n. So this is a k tuple of complex numbers. I rescale it properly, and properly in this case means n to the minus a half. You have to think of this square root of n as like central limit theorem. This is a sum. So if I rescale it properly and I ask, what's the probability that this k tuple hits this given set in c to the k? This limit exists when n goes to infinity, and it's precisely this p f t of A. So the existence of this limit implies the existence of this one, where lambda is the Lebesgue measure, and you see the set A here the set A in C2 is a product of two balls. The complement of a ball of radius R1 here times the complement of a ball of radius R2, and the t is basically 1/2 1. Okay. So this is the statement. This theorem, this is the final theorem of a series of papers. There is a very beautiful result by Jens Markloff in 1999, and then there is a result by myself in 2011, and then together we did this with the general F, because the classical theta sums correspond to this cutoff function. So you see there is a cutoff here. It's decreasing fast enough so the sum makes sense. If you take a sharp cutoff, like the indicator of 0, 1, you get basically a sum from 1 to n. Okay? And we know a lot about this limiting probability distribution. From probability theory, you might see this as a sum, like a weighted sum of dependent random variables. So alpha is random. So this is a sum of random variables. If they were independent or weakly dependent, then you would expect a central limit theorem. So you divide by square root of n, and you get a Gaussian in the limit. Here you do not get a Gaussian. The scaling is still square root of n, so it's something that physicists might call anomalous diffusion. I mean, some people like to call it anomalous diffusion, but the limiting distribution, it's not Gaussian because we know the tails of these distributions here, and they depend. I mean, they have polynomial tails. This distribution of order, like the complement of a ball of radius r, goes like 1 over r to the 4. So it's polynomial. It's not Gaussian. So it is not a central limit theorem, or it's a different type of central limit theorem. And the next order in the tails depends on the regularity of f. So you give me f, I can tell you a lot about these measures. And in particular, they need not be fully supported on c to the k, which means that in here, if you, instead of looking at this, if you change, you want the first guy to be less than something and the second guy to be bigger than something, if you choose this R1 and R2 properly, this probability is 0 because of the dependence. You cannot make this small without making this small as well. So we know a lot about this probability distribution, and they imply a bunch of results, for example, in quantum mechanics. And these theta sums, or generalized theta sum, or generalized Weyl sum, if you change the two into another power, they have an immense number of applications, number theory, physics, so I don't have time to talk about it. So to prove these theorems, I have two different approaches. One is jointly with Jens Markloff. It's using equidistribution of orocycles in the spirit of the work by Sarno.
But in that case, these measures would be volumes in homogeneous space.
Yes. So basically, these measures appear naturally as push forward of the natural Haar measure on some natural homogeneous space, push forward with different functions that depend on t and f. So they are like all manifestations of one single Haar measure on some homogeneous space. There is another approach in my thesis where if you do this for the sharp cutoff, then you can work with continuous fraction expansion of alpha. And that goes back to Harding Littlewood and many, many people, yes.
So that's more down to
Yeah, exactly. You don't need any homogeneous space, but you need a lot of exactly. I mean, that approach proves existence of the limit. Just existence. Yes, it's very. You have to work very hard with symbolic dynamics basically and some mixing. But if you want to know the asymptotic of the, yes, yeah.
If k is 1 and you have a sharp cutoff, is it Gaussian?
No, I'll tell you what it is. So if you look at the measure of those alpha 0, 1, such that divide by square root of n, take s n sharp cutoff. So it's 0, 1. That's a sharp cutoff, bigger than r. So that's what you want. This is equal to some constant, which is 4 log 2 over pi square, 1 over r to the 4. So this already tells you that it is not Gaussian, plus beta of r to the minus 6.
This is a pseudo-random.
This is the sharp cutoff. If you replace the sharp cutoff by like a triangle function, which is slightly more regular, this becomes different constant, and this becomes minus 8. If you replace it with a smooth, like e to the minus 2 pi u square function, then you get any decay you want.
This is immediate from the standard.
Yes. Yeah, but if you want to see this as a random process where t, instead of being discrete, ranges continuously between 0 and 1, then you have to work. You have to figure out how the tails behave. Yes. This is basically the finite dimensional version. Yes. So it is not Gaussian because the tail is heavy. So only 4 minus epsilon moments exist, And
You can do similar things for cubics or not?
cubic is like, no, we don't know what's the homogeneous space. We don't even know, it's not even proved that for a positive measure set of alpha, the corresponding cubic has to grow like square root of n. That's even like a more primitive question. Is square root of n the right scaling? People believe it is, but we are far from there. There is a recent...
If it cannot naturally, this would correspond to what equation? I mean, it wouldn't really fit exactly in the Schrödinger discussion.
Oh, no. I mean, if you just look at this now and you want to work with cubic, it's a much harder question. And we don't know if the square root scaling is the right one. I mean, we think it is. There were some recent progresses by Heath Brown where they can bound this, but the power is not the optimal or the expected one yet. So.
No, but your 2 norm is you have to normalize your 2 norm, so I don't see what other scaling you can put in there.
Yes. Yeah. But certainly there is no homogeneous space known.
No, but your second method may have a chance just doing the root force analysis.
Yeah.
This is what heat browns do.
Okay, I see.
I think
But Heath Brown isn't he assuming like ABC conjecture? And
some of these upper
yeah. Yeah. So.
The point is, the homogeneous space comes from the fact that the theta function is a modular form.
Yeah.
That is, a certain smoothing of this lives on a certain space.
Yes.
So he doesn't have a complete theorem. He's wrong.
No.
What does he prove?
Okay, so
Yeah. He proves bounds,
let's first
not distribution.
Then